Okay, so imagine this, right? A world where we can predict prime numbers. Not just find them, but like know exactly where they'll show up.
Yeah.
We're diving deep today into something called the Riemann hypothesis.
Mm-hmm.
And you sent over some really interesting stuff for this one. Articles, forum discussions, even like a whole lecture transcript.
Wow.
It's this idea that the distribution of primes, those like building blocks of all other numbers, that it's not just random.
Yeah.
It's not chaos. It's actually following some hidden order.
A blueprint.
Yeah. And the key to that blueprint, to that order, might be something called the Riemann zeta function.
It's a fascinating concept, really. Think of it almost like a mathematical lens,
Oh, okay.
bringing those patterns, the subtle patterns of prime numbers, into focus.
Right. Because on the surface, they do seem totally random and unpredictable.
They do.
But this hypothesis suggests there's like an underlying structure to it.
Yes.
And the key to that structure could be the zeros of the Riemann zeta function. So the specific inputs to this function that make the output zero.
Yeah, and what's so fascinating is these zeros, they're not just random points.
Yeah.
The hypothesis states that they all line up perfectly on a single line, on a complex plane.
But hold on. A complex plane.
Mhm.
Now, I vaguely remember struggling with imaginary numbers back in school.
Yeah.
What do those have to do with prime numbers?
Well, it is a leap,
Okay.
but a really brilliant one. You see, the Riemann zeta function, it doesn't limit itself to our familiar number line.
Oh, interesting.
It goes into the realm of complex numbers.
Right.
Which have both a real part and an imaginary part.
So Riemann took something that seems pretty simple, right? Adding fractions
Uh-huh.
and like catapulted it into a whole other dimension. Literally.
Literally, yeah.
This is how we can see these connections to primes that were hidden before.
Mhm.
But why zeros? Why are the zeros so important?
Well, you can almost think of each zero of the zeta function like a tuning knob, a tiny little adjustment that makes the formula for predicting prime numbers more accurate.
So the more zeros we find that fall on this line, the more accurate that prediction becomes.
Exactly. And if the Riemann hypothesis is true, and all the zeros line up like we think they do, this formula becomes incredibly precise. It would be like having a map to every single prime number.
Okay. So you said all the zeros, but I noticed earlier you said non-trivial zeros.
Yes.
Are there trivial ones too? What's the difference?
Well, think of the trivial zeros as like the ones we can easily account for.
Okay.
The predictable ones that don't really tell us anything new.
Yeah.
It's the non-trivial zeros that are interesting.
Okay.
Those are the ones that reside in this special region on the complex plane that we call the critical strip.
And this Riemann hypothesis claims that they all fall on a line right down the middle of that strip.
Exactly. A line where the real part of that complex number is always 1/2.
But here's the catch. No one's actually proven that, right?
That's the core of it.
Yeah.
Even though we've tested trillions of zeros
Oh, wow.
with computers, and they've all fit the pattern.
Yeah.
Proving it mathematically for all zeros, infinitely many zeros, that's a whole other challenge.
So we have this idea that prime numbers that seem random on the surface could follow this predictable pattern.
Right.
But to prove it, we have to solve this incredibly complex math puzzle
Mm-hmm.
involving zeros on a line in a complex plane.
It's a journey.
Tell me, how did we even get to this point? Where does this zeta function come from?
Well, we have to give a lot of credit to a guy named Leonhard Euler,
Euler.
a mathematical giant who really paved the way for Riemann's work.
Every math enthusiast has at least heard the name.
Right.
Didn't he explore, like, infinite series?
He did, and his work was groundbreaking. He delved into the properties of these infinite series,
Okay.
particularly when those sums actually approach a finite value, when they converge.
Yeah.
And that work led him to an early version of what we now call the zeta function.
So Euler was already playing with infinity and had, like, his own version of the zeta function.
Yeah.
But what did Riemann do that was different?
Well, Euler's zeta function was limited to real numbers, numbers greater than 1.
Right.
Riemann's genius was to extend that into the realm of complex numbers,
Ah, okay.
using something called analytic continuation.
Analytic continuation, that like extending a pattern beyond its boundaries.
That's a great way to put it. Imagine you have a piece of a puzzle.
Yeah.
And you can see enough of the pattern to figure out what the missing pieces should look like.
Okay, yeah.
And then you can recreate the entire image. Analytic continuation does something similar with functions.
So Riemann took Euler's work as a starting point and expanded it into this incredible tool
Mm-hmm.
that let him see these non-trivial zeros. But how do we know these zeros are actually connected to prime numbers?
Well, that's where things get really interesting. Riemann himself developed this remarkable formula. We call it the explicit formula.
Hmm.
That directly links the zeros of that zeta function to the count of prime numbers.
So this formula basically says we can use these mysterious zeros to count prime numbers.
In essence, yes. Each zero contributes to making that formula more and more accurate.
Wow.
It's mind-boggling.
And if all the zeros align like the Riemann hypothesis says they should, this formula becomes even stronger, right?
Exactly. It means that the distribution of prime numbers actually follows this surprisingly predictable pattern. It would be revolutionary.
This is where it starts to get really exciting. But I'll admit, this idea of complex numbers and zeros being the key to unlocking prime numbers, it's still kind of mind-bending. What are the biggest challenges that mathematicians face in trying to prove this? What makes it so hard?
Well, one of the biggest hurdles is the sheer scale of it all. I mean, the Riemann hypothesis is a statement about infinitely many zeros.
Right, infinity. So
Right.
no matter how many zeros we check and find on that line, there's always a chance that somewhere, way out there, a rogue zero breaks the pattern.
Precisely. That's why we can't just rely on brute force computation alone. We need an elegant mathematical argument that holds true for all zeros, no matter how large or complex.
Okay, so brute force isn't enough. You mentioned analytic continuation earlier. A lot of our sources pointed to that as a key challenge, too. How does that fit in?
Well, remember, analytic continuation lets us extend a function beyond its original domain. In the case of the Riemann zeta function, it lets us define it for almost all complex numbers. That's how we find those non-trivial zeros.
Mm.
But it also adds a layer of complexity.
It's like opening a door to a hidden room, but you're not sure what you'll find inside.
Exactly. Analytic continuation provides a more complete picture, but it also makes the zeta function much harder to analyze.
So we've got the challenge of infinity, the complexities of analytic continuation, and then there's the inherent mystery of prime numbers themselves. They've been puzzling mathematicians for centuries.
Absolutely. Prime numbers are both fascinating and frustrating. They exhibit patterns, but there's also an element of randomness. That unpredictability is what makes them so difficult to pin down with a single formula.
Kind of like trying to predict the weather, right? You can see general trends, but there's always a chance of a sudden storm.
Perfect analogy. And that inherent unpredictability is a big part of what makes the Riemann hypothesis so challenging. It's a search for order in apparent chaos, a quest to uncover a hidden structure within something that has defied simple explanation for so long.
But even without a complete proof, our sources suggest that the pursuit of the Riemann hypothesis has led to some amazing results. It's like they say, it's not the destination, it's the journey.
I love that, and it's so true. The quest to solve this problem has led to breakthroughs in various mathematical fields, from complex analysis and number theory to random matrix theory and even quantum physics.
Wait, quantum physics, that's a long way from prime numbers. So even if it's a theoretical pursuit, the Riemann hypothesis has the potential to affect our lives in very real ways.
Absolutely. That's one of the most exciting things about mathematics. It's a search for knowledge and understanding, but that knowledge often has unexpected applications in the world around us.
Our sources mentioned a bunch of attempts to prove this hypothesis. Everything from brute force computation to exploring connections to geometry and physics. Let's dig into those a bit. What about those early attempts using brute force? I imagine with computers we could just check tons of zeros, right?
Right. Early on, mathematicians tried to check as many zeros as possible to see if any of them deviated from the critical line. With computers, they've been able to verify trillions of zeros, and none of them break the pattern.
But like we said before, brute force can't completely solve this because we're dealing with an infinite number of zeros. What about some of the other approaches?
Well, some have tried to find geometric interpretations of the Riemann hypothesis, hoping to visualize the zeta function and its zeros and see if there are any hidden patterns there.
So they're trying to translate this really abstract mathematical concept into something more concrete, something we can actually see.
Exactly. The problem is that the zeta function and its zeros exist in the world of complex numbers, which are very hard to visualize. Plus, analytic continuation makes things even more complex.
Okay, so brute force isn't enough. And geometric interpretations haven't yielded a definitive proof either. What about those connections to physics? Have they offered any solutions?
The connections to physics are still being explored, but they are really exciting. Some researchers see parallels between the distribution of non-trivial zeros and the energy levels in quantum systems. Others are investigating links to random matrix theory, which studies complex systems with lots of interacting components.
So maybe by understanding those physical systems better, we might gain some insights into how the zeta function and its zeros behave. It could be a backdoor to a solution.
That's the hope. The fact that these connections exist at all suggests that the Riemann hypothesis might be more than just a mathematical curiosity. It could point to a deeper structure underlying both mathematics and the physical universe.
That's a pretty profound thought. But let's bring it back down to earth for a minute. What specific progress has actually been made towards proving the hypothesis?
Well, despite not having a complete proof yet, mathematicians have made significant strides. They've developed techniques to estimate the number of zeros on the critical line, and these estimates align incredibly well with the Riemann hypothesis.
So it's like we're getting closer, narrowing down the possibility.
Exactly. Each step forward brings us closer to either proving or disproving this remarkable hypothesis. And the really cool thing is, all along the way, we're making incredible discoveries that deepen our understanding of mathematics as a whole.
Our sources mentioned a few specific areas of advancement. For instance, they talk about something called the Mertens function, and it's linked to the Riemann hypothesis. Can you explain that?
Sure. The Mertens function is a fascinating object in number theory. It's closely related to the distribution of prime numbers, and there's actually a way to rephrase the Riemann hypothesis in terms of this function.
So proving something about this Mertens function would be the same as proving the Riemann hypothesis. That's wild.
It just goes to show how interconnected different mathematical concepts are. The Riemann hypothesis isn't just a standalone problem. It's deeply woven into the fabric of number theory. Solving it would have huge implications for the entire field.
It's like realizing that tugging on one thread in a tapestry can affect the entire design. But if you had to sum up the core difficulty of proving the Riemann hypothesis, what would you say it is?
At its heart, the difficulty lies in bridging the gap between the finite and the infinite. We can check a finite number of zeros and develop theorems for specific regions, but the Riemann hypothesis makes a claim about infinitely many zeros across the entire complex plane.
So we're using our finite tools and methods to try to grasp something that's inherently infinite. That sounds like a recipe for a headache.
It certainly can be. And that's the ultimate challenge. We need a new perspective, new tools, and a new way of thinking that can truly encompass the vastness of infinity.
It's a beautiful struggle in a way.
Yeah.
This clash between the finite and the infinite is part of what makes the Riemann hypothesis so captivating. So what's next? Where does the research go from here?
Well, the Riemann hypothesis is like this beacon, right? Drawing mathematicians to its mysteries.
Yeah.
So some are digging deeper into those connections with physics, hoping that insights from quantum mechanics or even random matrix theory might help illuminate the problem. Others are pushing the limits of computation, trying to verify the hypothesis for even more zeros.
So they're kind of attacking it from all angles.
Right.
Brute force, theoretical frameworks, even looking for clues in the quantum world. It's like a big scientific adventure.
It really is. And there's this sense of excitement, you know?
Yeah.
Some mathematicians believe we are on the cusp of a major breakthrough.
Oh, wow.
New tools, new techniques, they're being developed all the time. And the collective knowledge is growing so fast.
It's inspiring, isn't it?
It is.
This dedication, ingenuity of these researchers.
Yeah.
Driven by this quest to understand prime numbers.
It really speaks to that enduring power of curiosity, don't you think?
Absolutely.
That pursuit of knowledge for its own sake.
Yeah.
This desire to unravel the secrets of the universe.
It's amazing. And, you know, as we've been going through all this, it's made me think about how much we rely on prime numbers in our daily lives.
It's true.
Encryption, online security, all sorts of things.
Yeah, prime numbers, they're really the backbone of modern cryptography.
Uh-huh.
And while a proof of the Riemann hypothesis wouldn't necessarily, break those existing systems,
Right.
it would definitely deepen our understanding of prime numbers.
Right.
And it could really influence the development of new, even more secure encryption methods.
So this seemingly abstract math puzzle could have some real-world implications
Absolutely.
for our digital world.
Yes.
It's a good reminder that even the most theoretical pursuits can have unexpected consequences.
Exactly, and that's part of what makes this whole thing so fascinating.
Yeah.
We're exploring these fundamental foundations of math, but those foundations have these connections to the real world in
Right.
ways we might not even fully understand yet.
Well, I think we've covered a lot of ground today.
We have.
Prime numbers,
Yeah.
Euler's Zeta function, Riemann's expansion, those elusive zeros,
Yeah.
and this ongoing quest to conquer this mathematical Everest.
Yeah, we've seen the challenges, the progress, the potential impact, and, just the sheer audacity of human curiosity driving it all.
It really is a story that's still being written, isn't it?
It is.
And who knows, maybe one of our listeners will be the one to write the next chapter.
Wouldn't that be amazing?
Maybe they'll be the one to find the missing piece of the puzzle, that spark of insight that unlocks the Riemann hypothesis.
That would be incredible. But
Yeah.
honestly, even if that day never comes, the journey itself is a testament to the power of human ingenuity and
Yeah.
this relentless desire to understand.
So everyone listening, keep those minds curious, keep those imaginations fired up. The world of math is full of wonder and endless possibilities.
Right.
And who knows what fascinating discoveries are waiting for us just around the corner.
Exactly.
Until next time, happy exploring.